Okay, in this chapter, we're going to look at a new type of regression model called the logistic regression model. We're going to see that there are a lot of similarities to what we saw with ordinary linear regression, but there's also a lot of differences. The big idea of when you want to use this type of model is when you're trying to predict a variable that's binary. Okay, so a binary response variable is going to clue you in to use the logistic regression model. And in this model, the explanatory variable can be categorical or quantitative. In this chapter, we're going to just start with a simple case of where we have one explanatory variable that we're using. So two examples might be you want to predict whether or not a student is accepted into graduate school based on their GPA. Again, I hope you see that this response variable, acceptance, is binary. Or we might want to predict whether or not one has high cholesterol based on their weight. And so again, whether or not one has high cholesterol is binary. We're going to see the important idea that's going to look a little bit different, but with binary response data, we're going to need to do a transformation that involves the log function. Okay, so the first example that's in the text is called a data set called Losing Sleep, and it contains data on 446 teens aged 14 to 18 years old. Each was asked, on an average school night, how many hours of sleep do you get? And what the researchers did is they looked at teens who slept at least 7 hours, and if that was the case, they were marked as yes and then coded as a 1 in the data set. And if they didn't sleep at least 7 hours, they were marked as no and coded as 0. Okay, so here's just some summary data. You can see a breakdown here by age, and this is the number of people who slept fewer than 7 hours, 7 hours or more, and then the total responses. So if you look here, these proportions down here is just a percentage in the sample who slept more than 7 hours. So 34 out of the 46 14-year-olds, or 74%, slept more than 7 hours. Likewise for the 15, 16, 17, and 18-year-olds. Okay, so here's a graph of that shows the data of the age data according to proportions. Okay, so that's a scatter plot which shows this. So just a caution, you might say, oh, this looks linear, and I'm going to fit this set of data with a linear model. Okay, but you do not want to do that, and I'm going to talk about why you don't want to do that. So again, you might want to say, oh, the proportion of successes or yeses looks like it should be linear, so I might want to use this model. We're going to see this part's okay, but over here we're going to have an issue because this is estimating the proportion of successes, and we're going to see that with a linear model, it's going to quickly, if we were to do this, predict values outside of the range of true probabilities, right? It's going to predict values for probabilities that are larger than 1 or less than 0, and that's problematic. Okay, so just see, let's say naively you incorrectly fit this data with a linear regression model like I have here. Okay, and so what I was just talking about a minute ago, you can see that for someone who's 1 or 2 years old, if you were to continue this line, you're going to predict their probability of saying yes is bigger than 1, and that can't be the case. And similarly, someone who's 40 years old, the model would predict a negative probability, and we can't have negative probabilities. Okay, so to avoid this issue, we're going to need to use what I mentioned earlier, a transformation. Okay, and it's something called the logistic transformation. And what's nice about it is the model always gives fitted values between 0 and 1. And since we're predicting probabilities whose values need to be between 0 and 1, this is exactly what we need. Okay, so you can see this is logistic transformations will always give us an S-shaped type of curve. So it's going to bound between 1 and 0. And our explanatory variable in this case is age. Okay, so just a little review on odds and log odds, and I would refer you to page 417 in the book to also do a little more review with odds. Okay, so before I get into that, this paragraph, just notice a couple things. Let's say the probability of success is 1/5, and pi stands for probability of success. So we can convert this into odds. Okay, the odds is just pi divided by 1 minus pi, and you would get 4/5. So the way you want to think about a probability, right, is there's a 1 in 5th chance of probability of being yes, excuse me. What the odds are, you can think about saying, is given a sample of 5 people, we expect 1 yes and the remainder 4 no's. Okay, and so this shouldn't be 4/5, sorry, this should have been 1/4. So what the odds are saying is, yes, 1 yes for every 4 no's. Okay, so we're going to see, as I mentioned before, we're going to need this logistic curve. And so we're going to be interested in taking the log odds. Okay, so the log odds is just log of pi divided by 1 minus pi. Oh, by the way, log, for everything we're doing, I'm always going to be referring to the natural log. Could you use a different base? Yes, but it's just simpler to use the natural log. Okay, so I'll show you how to do all of this in Minitab in a moment, but just a couple of things before we do that. So, by the way, when you see this output, what Minitab calls y prime, note that this is just the log of the odds, what I was talking about a minute ago. So this is, since it's fitted data, we'll put a hat over pi. So it's the log of the probability of success divided by 1 minus probability of success, which is your estimated odds. Okay, but that's what the y prime is. Okay, so note in this top graph, this is giving us the log of the odds versus age. And the bottom graph is estimated probability of saying yes based on age. Okay, so we can go back and forth between these two graphs just by making a transformation, and we'll see that in a minute. So we can take this logistic graph, and if we transform over to the log odds instead of probability of success, we get this linear relationship, and that's helpful. Okay, so here's the only new feature right now that you need to be able to do in Minitab is to get this logistic regression. So if you go to regression and then scroll down to binary logistic regression and then click fit regression model, this pop-up window down below will appear. Okay, and you want to put in for your outcome, that was what our data set was calling probability of success. That will go here. And then you're predicting based on the child's age, so that goes down here. And that's it. And so if you run that, you'll get the model that I just had a minute ago. Okay, just a little bit more about log odds before we move on. Just let me make sure everybody's clear. Again, log odds is this definition. So for various probabilities or probability of successes, here's just a table of potential ones, right? 1/20th or 1/10th or 1/5, these are all probabilities. We could rewrite each of these probabilities as a decimal, and then we could get the corresponding odds. So as I mentioned a minute ago, to say some event has a 1/20th chance of being a success, the other way to think about that is out of 20 people, let's say, we expect 1 success and then the remaining 19 failures. So we could do that for all of them. And then finally, we want to take the log of the odds, and here's a log of the odds. So I mentioned this for 2 reasons. If you look at these probabilities, these values of pi, with their corresponding log odds, so in other words, this row versus this row, and graph them, you can see that the graph that you get is an increasing function. And so we have a nice one-to-one relationship between probability of success and log odds. What that means is, given any probability of success, there's exactly 1 log odds that corresponds to it, and vice versa, except for 0 and 1. But we can fluidly go back seamlessly between log odds and probabilities and work from one to the other. The second thing I want you to notice is that this log odds, this is a strictly increasing function, so log odds can take on any value, right, between minus infinity and infinity. So if we want to use a linear predictor, and that's what we want to do in this, we're going to want to look at predicting log odds based on a linear function. Okay, that's not going to be a problem. Okay, so because what I mean by that is if this linear predictor has a negative value, no problem. We can always, the log odds is defined, and likewise, if this predictor gives us a value bigger than 1, log odds is also defined. More details about this are given in the text, so you should read that carefully. Okay, but this is really an important slide that summarizes our new model. So all what we've been doing so far has led us to this. This is our logistic model, often called the logit, its logit form. And notice that it really is it has linear terms on the right side. That should look familiar, beta naught plus beta 1x. And our predicted values here are the log odds. Okay, if you just do some minimal algebra from this equation by taking base e to both sides, you get this. And then if you do the algebra and solve, it's just a simple algebra exercise, solve for pi, what you end up getting is what I'll circle in blue, and this is equivalent to this, okay? So sometimes we're interested in predicting the log odds, and this formula will be helpful. Sometimes we want to predict probabilities, and so the blue formula will be helpful, the probability form. But notice they are equivalent, so you can use either one. When Minitab gives you the output, Minitab is giving you the output in the logistic or the logit form. Okay? Okay, so let's look at one more example. The Med GPA data set that's in the data set in the book. It has data on 55 med school applications from liberal arts colleges in the Midwest. And for each applicant, the students were either accepted or not. So 1 means they were accepted, 0 is they were not accepted. But it also gives other measures, for instance, their college GPA and their scores on the MCAT exam. And what we're going to be interested in doing is to see if these variables can be useful predictors in determining whether or not a student was accepted into med school. Again, our response variable is binary. It's whether or not the student was accepted. So we definitely want to think about logistic regression as opposed to the ordinary regression we studied earlier this semester. Okay, so I'm just giving you, we're going to first be interested in fitting the data. We've chosen the logistic model. We want to be able to fit it, and then later in the text, assess and then use it. Okay. So the graph on the left gives it's just showing the relationship between MCAT scores and GPA. And you can see that students who did well on the GPA did well on the standardized acceptance tests. Students that didn't do well on the GPAs didn't do well on the MCAT. So just understand that there's a linear relationship, pretty strong linear relationship. And if we wanted to, we could predict MCATs based on GPA. Okay. But let's say we want to predict the probability that a student is accepted. And again, that's binary, so we're going to want to use a logistic regression model. I'm going to keep it simple to start with, and we're just going to predict acceptance based on the student's GPA. Okay. So you can see here all of these dots are students that were not accepted into med school and their corresponding GPAs. And up here, these dots correspond to students who were accepted into med school, that's a 1, and their GPAs. And no surprise, you can see that their students who were accepted had higher GPAs overall than students that weren't. Okay, so we want to fit this data set with a logistic model, and here it is using Minitab. Okay, so again, keep in mind that if you follow the Minitab steps I showed you, you should get this. Okay. And actually, Minitab, I think I said earlier, doesn't give the probability, but in fact it does. So there's the probability model, and here's the logistic model. Keep in mind, again, folks, that y prime stands for log of pi hat over 1 minus pi hat. Okay, it's a log of the estimated odds. That's what the y prime is. All right. So let's just make a prediction now. So I'd like us to think about, can we estimate the chance of acceptance for a student who has a 3.6 GPA? Okay, well, thanks to the Minitab output that we got, that's pretty straightforward to do. So this is a population model. The fitted model looks like this. Y prime, again, is log of pi hat over 1 minus pi hat. The estimate for beta naught is 19.21 minus 5.45, this is the estimate for beta 1, times GPA. Okay? And so if you exponentiate both sides, just to do a little algebra so you see where it's coming, although Minitab will do a lot for us, if you exponentiate both sides of this equation, you get this. And again, we're going to try and predict a student who has a 3.6 GPA, so I'm going to put that in here. So the stuff on the right, that just simplifies to 1.51. You can check that. Okay, so you could solve for pi, and if you solve for pi hat, what you'll end up getting is 1.51 over 1 plus 1.51, which is equal to 0.60. So this is saying that we expect that a student who has a GPA of about 3.6, they've got about a 60% chance of being accepted into med school. Okay, notice that, by the way, folks, we can get that probability from up here as well. Okay, so this is just a brief introduction into the idea behind logistic regression and how do you get the logistic remodel using Minitab.